Hey, Aiken, my dude. How you been? Hope you've been okay. Alright, let me get set up here. There we go. Yes, Yusuf! Yes, Yusuf, how we doing? I hope we're doing absolutely fantastic. Aiken, I hope you're doing absolutely fantastic. Whew. Look at that, we got some legends here in the chat. Very good to see you guys. There we go. I think that works. Huh? Oh. Okay. Adjustments need to be made. How you doing, everybody? Let me switch to my other camera here. Here we go. Hey, how's everybody doing today? I hope everybody is fantastic. All right. Hopefully everybody is doing great, great, great. Now, hopefully my stream doesn't shut down on me today. I'm a little worried, in all honesty. I'm a little worried that my stream may shut down on me, but if you move, you gotta try. As you know. This thing, let me tell you, this thing. Cross my fingers. What's my thoughts on the hashtag game yesterday? I think that I only got to see the first 30 minutes, so I haven't seen Gleedy's red card. But the first half they played really, really well. They played outstanding in the first half. Like they had a lot of chances. They were moving the ball well, and then I guess from what I heard, Glee's red card happened and it just kind of collapsed after that. They were lucky to get the goal there from Jesse, but then 10 men on the field and things were thrown into disarray. And it just shows the level of competition that they have to play through. They have the chops to hang with the competition in this league in the Isthmian North. It's just a matter of at the end of the day, are they going to be able to put it together and to put it into a string of wins? So, you know, we're hoping for the best for the team, and there's certainly things and areas that they have to improve in. And I'm sure Devs is going to have good long chats with a lot of the players just to make sure that they're all on the same page for the next game. So that's what I think about hashtags game last time. Obviously being disappointed, but again, it's a learning process here when you're going up through the leagues as fast as we have. So it's sometimes going to be you're going to hit that brick wall. You're going to have a difficulty in terms of adjustment, but you're going to have those times where you're going to be frustrated, and I think that's okay. That's the growing process of any good team. So that's what I feel about yesterday's game, and probably what a lot of fans are thinking as well. So at least I think so. I don't know. What do you think, Yusuf? I know the record. 0-1-2 doesn't mean things are over. Our next game is against Canby Island. So our next league game, not our FA game. The big test will come in the following week, as I'm looking at the schedule right now. Will be Malden and Tiptree because they're top of the table, and so that's gonna be a good test to. Or actually, no, I take that back. They're fifth now. Probably be top of the table if they win their next match, though. So I'll bring this up on screen here. So here we are right now. We are 1 point, 3 games, 1 and 2. Gray's Athletic, Barking, Whittam, and Sudbury being top 4. Malden Tiptree have yet to play their third game, so once they play their third game against Haybridge, we'll see where they're at. But they're a very strong team. Let's see where we're at in a couple games from now. It's certainly possible, Yusuf. It's certainly possible. Like I said, we have the capability. We have the squad. Now we got to put the pieces together. That's the whole goal there, Yusuf. That's the whole goal. It is not an easy league, and we're not going to be assuming that this is going to be an easy league, or we're just going to pick up points left, right, and center. But it's a nice long season. Okay, it's a nice long season. There's 38 games in this season, so you know there's many more games to go, many more points on the table. So let's see where we're at once we are our way up there. So give it some time. Give it some time, Yusuf. Where's that button? There it is. All right. Good. All right. How's everybody doing today? Oh, it's 11 o'clock already. Jeez. All right. Already 11 o'clock. Ooh. Uh-oh. No, what happened? Yep, it's true. Let me go and grab a drink. I'll be right back. Then I'll get started here. So, go grab a drink. A second. Here. Oh. Humma. All right. Okay, we'll do a little bit of intro and then we'll get started here with some new material. This shouldn't be, at least I don't believe this material here to be too hard. Pretty straightforward when it comes to statistics. So, quick, up in some rings. Supplements to keep the day going. All right, folks, healthy is wealthy. All right, let's do some intros here, and we'll go ahead and get started with this. Hello, Jasmine. How we doing? Okay, let's get started today. Welcome back to Tuesday. Hope you're having a nice weekend. All right. So today, everybody, good morning. Good morning, everybody. Hello. It is absolutely fantastic to see you all here once again. All right. Fantastic to see you here. I hope everybody had a absolutely brilliantly wonderful weekend. We are back here. So just to cover up last time here, everybody, Carla, Cindy, Sneaky, Jasmine, Isabella, great to see you all. Wonderful to see you. Good morning to all of you. So last time we went ahead and did most of Chapter 1. So most of Chapter 1 was done. We didn't do a couple of questions here. We're going to finish up those last couple of questions, which will finish up Chapter 1. And then we're going to get into the actual meat and potatoes of what we're doing here today, which is going to be Chapter 2, which is actually numerical stuff, you know, with numbers, you know, actual real numbers. So it's kind of amazing. All right. In any case, let's go ahead and finish off Chapter 1. Look at the handout here from last time, and we'll move our way forward. Stuff is hard to do. All right. Let's go to the big board, and let's see what we're... All right. All right, so this is where we're working with. Last time we went through all the things. We got up here to question 8 from the handout, second half of the handout, I should say. All right. So we talked about some of these last week, and again, I just want to reiterate here from what we discussed here last week to this week. So hopefully this shouldn't be overtly too hard. Okay. So much adjustments. Okay, so let's take a look here at number 8. Number 8 talks about what type of experiments are there. We did talk about this last week. This is in relation to clinical trials. We talked about, again, um, we talked about single blind and double blind. All right. These are pretty popular type of experiments. All right. So, for example, again, single blind is like one per side knows who got what, and double blind means neither side knows who got what. Like I said, I'm not going to expand on these too much here, but again, these are type of experiments that we discussed here last week, so that's why I'm not going to really expand on it in this case. All right. Now, let's look at number 9. What is a completely what is a completely randomized design? A completely randomized design is exactly as it sounds. You randomly design the experiment. So randomly design the experiment. Okay, um, with a random, say, control group and random treatment group. Okay, so that's basically what it is. Again, everything is assigned to a random treatment. Everything is assigned to a random control. So again, truly randomized in your experiment. You're still like testing a drug, but it's like nothing's really different. You know, you're testing the drug, but again, you're just kind of going, hey, you get the treatment, and hey, you get the control. But in actuality, you probably don't know who got what. You're just like, here, take this, here, take this, and here, take this. So again, that'll lead to kind of like that double blind sort of situation. Again, not going to expand on this too much here, but it is what it is. All right. Now, number 10 here, which is the last question here and the last part of chapter 1 before we move into chapter 2, which is what is a matched pairs design? Okay, so basically, this is something we will see, let's say, where maybe really later on in the textbook here. We'll talk about this idea of a matched pairs design. But the actual kind of overview here is basically it's an experiment where uh, one person from the control group is paired with one person from the treatment group to compare and contrast with. So this is really important here for this in regards to, let's say I'm doing a clinical trial for a drug. Let's say sometimes they'll ask for people that have similar health histories or similar health backgrounds. So for example, let's say this drug was to handle diabetes, something like that. And you're like, okay, you want to be able to manage diabetes, and so maybe one person in the control group who's not going to get the experimental drug has, say, type 2 diabetes. The second person in the control group who has type 2 diabetes as well, again with the similar health profile as the first person who's in the control group. And then you can see how does the drug affect the person who got the drug, the experimental drug, and the person who did not get the experimental drug, because they have similar health backgrounds. And then that way you could see, okay, what's the drug interactions, was it effective or not? And so this really, really helps out with a lot of important results to see, what's the effectiveness at the end of the day with people who have those kind of things, especially for your target group. All right, so that is an experiment. That is a matched pairs design at the day. All right, good stuff. Okay, now, are there any questions over chapter 1? Any questions at all? know if you have any questions about chapter 1. Again, type no in the chat if you have no questions, you want me to move on, or if you do have a question, let's go ahead and type it out. Okay, what's your question about homework there, Sarah? Okay. When is homework due? Homework is due whenever we finish these first 3 chapters, or first, yeah, 4 chapters. So I will announce when the homework is due, and then when the homework is due, the test for that will be due as well. So if I haven't said anything about the homework there, thank you, Rhino, for the follow, by the way. Um, uh, yeah, that's yes, Sarah, that's correct. So whatever chapters test 1 covers, if that's chapters 1 to 4, then those are that's exactly what the homework is going to be due, is chapters 1 to 4. All right. No, you're fine. You're fine. Let's keep it pace. It's okay. It's okay to ask. Like I said, I'm going to be as like I'll say here in this class, I will be as transparent as you want me to be. So, you ask me, I will be perfectly transparent. I'll be like, hey, this is why I'm doing things. This is why I'm doing this. This is why I'm doing that. Okay, if I don't explain why I'm doing certain things, then we got problems. Then you have no idea what the heck I'm doing. So I feel that we should always have an open line of communication in terms of why certain things happen. Some things I may say may not be happening, but you know what? It is what it is. I always try to be as forthright with all the information. So feel free to ask me anytime. Okay. Any other questions before I move forward? Any other questions? Okay. Go. Get into that part there. All right. So what I'm hoping for is that my stream does not shut down. That's what I'm hoping. Okay. All right. So let's go ahead and talk about chapter 2. All right. So here where we finished up chapter 1, that wasn't too hard to do. Let's start with chapter 2, the actual numerical part here. Now, of course, we're starting from the basics and kind of working our way up here when it comes to statistics. All right, and so to start off here with the basics here, let's take a look at question 1. Question 1 says, what is frequency and a frequency distribution? So this is the first thing that we're going to do here. In chapter 2, what we want to do here is to arrange data. Okay, so we're gonna have a whole, we're gonna have a data set of some things, and then we want to go ahead and arrange it in some way to organize it and then we can glean some results from organizing the data appropriately. First thing we have to understand is that the concept of frequency. Now, frequency here, basically, how often something occurs in a category, basically, or a classification. Whatever you want to call it. You could call it a category, you could call it a classification, you could call it, whatever you like, okay? But again, that'll be frequency. How many times does that occur? So a common example is, well, how many scores were in the 70s on a test in a class, okay? Oh, there were 5 scores, okay? And then you would write 5. All right, so that would be frequency. But we'll look at some examples here for sure. All right. All right, so what is a frequency distribution? All right, so a frequency distribution is basically a chart with the categories. So basically a chart or table, a chart or table with the categories and its respective frequencies. Okay, so that is going to be the frequency distribution for that. Okay, so just in layman's terms, frequency, how often something occurs in a category classification, and the frequency distribution will be that chart or table, whatever you want to call it, with the categories and its respective frequency. Now, let's talk about, let's take a look here at an example, okay, of a frequency distribution. Let's see how it works. So we're going to go over here to our good friend, and I'll lower this down here for just a second. All right. Let's go to our good friend here, the paint tool. All right, so the paint tool here is going to be our good friend. What we want to do. All right. Now, let's do an example here. Now, this example here is, let's say I have a set of test scores. So let's start off with some set of test scores. So, all right. So let me make up some random test scores, and then we're going to put it together in a frequency distribution. Okay. So let's start off with let's see, 73, 75, 9, and all right, here we go. Perfect. All right. So let's say these are a set of test scores here, just like so. Okay, so this is just a random bank of test scores. Now, just to let you know, by the way, about certain things, about how I'm going to be saying certain things here. I'm just going to be stating here this guy right here that you see here on the screen. This is effectively what we like to call a data set. Okay, so this is a piece of data. Okay, like 67 would be a piece of data. The entirety here of all the scores will be referred to as a data set. So you're going to hear me say that quite often in this class, that all of the scores here, so I'll just put this here as a side. You'll hear me say data item, which is just like one score, for example, and then data set, which is likely all the scores. Okay, so I'm just letting you know about that right now. It's on here. All right. Yeah, a little warm in my room. All right. Okay, so we have data item and data set. Okay, so now let's go ahead and arrange these items in an appropriate manner in a frequency distribution. So let's say I'm going to have here, I'm going to have scores. All right. And I have frequency here on right. Okay. So let's say I talk about the scores here. Now, let's be realistic about this, for example. Let me ask you here. Isabella, thank you for the follow. Let me ask you realistically, how would you arrange these scores? How would you arrange these scores? When we think about test scores, what do we usually arrange them as? Let me ask that question. You guys answer that for me. You guys put that in the chat. We talk about test scores here in general. How do we usually think about test scores? Okay, high to low, low to high. All right. Yeah, that's true. So you can put it in numerical order. I don't disagree with that. How about if we go from low to high or high to low, how would we arrange them? Let's think about. I want to hear your thoughts here. How do you think you would arrange just test scores here besides lowest to highest? So Totally understand lowest to highest. You take the lowest score, go all the way up from 1 to 100. Okay, 1 to 100. Okay, well. All right, but let's think about it a little bit more practically. Wouldn't think about average here in this case. We're just trying to arrange the data here in this instance. So the median and average are two different things, but wouldn't think of either of these things in this instance. So the way I would think about this, though, grouping them by letter grade, right? And you would say, okay, so let me go off that concept here for just a second. So you would think of it as like, okay, A, B, C, D, F, right? And you'd be like, okay, you get this score here, you get an A. This score here, you get a B. This score here, you get a C. Now, for scores here, I'm not going to label it as A, B, C, D, F, but we know that there's a range of scores that do reflect A, B, C, D, and F. Okay, we do know that for a fact. So let's say I go from, say, low to high. Let's just go with that. So if I were to go low, let's look at the lowest score here. The lowest score here is 52. Now, I would put in a range of scores to reflect, say, an F or a failing grade. So maybe that range of scores here would be 50 to 59. How many scores are in the 50s? Maybe I would do how many scores are in the 60s, 60 to 69. How many scores are in the 70s, 70 to 79. How many scores are in the 80s, 80 to 89. And how many scores are in the 90s, let's say 90 to 99. Yeah, each column is a letter grade, right? So you could say each individual score is a letter grade of some variety if you wanted to associate it like that. Now this is going to look a little weird on screen. You're like, chose these little categories here, like 50 to 59, 60s, 70s, 80s, and 90s. I'm going to talk about that here in just a second. All right, but I want you to take a look here. Why don't you guys help me out here? Let's take a look here. If we're talking about frequency, let's taking a look at the data set. How many scores that you see here are between 50 and 59? How many scores here are between 50 and 59, according to the data set? Okay, very good, right? So there's only one score here. Yeah, you would agree. I totally agree with everyone here. There's only one score here between 50 and 59. Seems fair. All right, let's look at the 60s. How many scores in the data set here are between 60 and 69? All right, we see 2 or 3. All right, let's take a look here. So we have 67, 61, and 69. Okay, so we indeed have 3. That's the intention here, Swedish. That's the intention here, Swish. We're gonna do that here. Let's look at 70 to 79. How many scores are between 70 and 79? We see B or 4. Let's see. 78. So 1, 2, 77, 73 and 75, 3 and 4. So according to our chart here, we should have 4. All right, so 4 here between 70 and 79. That's just fine. Going through this carefully here. How about 80s? How many scores we have in our data set that are in the 80s? 80 and 89. Okay, so we got 1. 4 is correct. Good. Very good. And then finally, let's look at the 90s. How many scores here are in the 90s? Again, I just randomly selected these numbers, so however it turns out, however. So 3, 4 actually. 1, 2, so 93, 91, 97, and 94. Okay, so here we have 4. That is correct. So we have 4 of each of those. Great. Okay, so what have we effectively done? We've effectively made a frequency distribution from our data set. All right, this is our frequency distribution right here. All right, no problem so far. Okay, any questions about that? We're going to expand upon this, by the way, but we'll use the same example here. Any questions so far? All right. All right, let's look at the next part if there are no questions. It's okay. All right, let's look at the next question here. That is the answer to that, Swish, is both. This is actually a class, a actual college math class, and this is free education for people who would want to take in the information. So if it helps, if it's just that little nugget of knowledge that you can take away for the day, saying that you learned something new, I will be just as happy with that, Swish. Okay. Let's take a good look here at number 2. All right, so how do we calculate relative frequency? All right, so relative frequency is pretty easy and straightforward. All right, it's really not too hard. Now, how do you calculate relative frequency? There is a small formula that goes with this. Relative frequency here is going to equal, specifically here, the frequency in the category just a silly question. Are we supposed to memorize all the I'm guessing you wanted to say definitions. I think that's what you meant there. Are we supposed to memorize all the definitions? The definitions would help. I'm not gonna lie. Definitions would certainly help. You may get a couple questions asked on the test regarding definitions, but it's not like you have to like super memorize them. So again, most of the definitions here, at least in the class, from the first chapter, are pretty self-explanatory. You know, they're pretty straightforward. So yeah, it shouldn't honestly be that big of a deal. I'm not gonna be like harping on you, like you have to know every single little thing in the whole wide world. No, there'll be certain things that we'll be doing in this class where it's like, okay, here's the formula, and I'm not expecting you to memorize the formula, but I am expecting you to apply said formula. Okay, so all right, that's basically how I'd probably look at it. Relative frequency is the frequency in the category divided by indirect one. Frequency in the category divided by the sum of the frequencies. Okay. The frequency of the category. All right. The frequency in the category. We could also, by the way, I actually will state this here. Category can also be called the word class. We'll talk about that here shortly. I hated school today. Hey, some days at school are gonna be such a bummer, but don't worry, tomorrow will be better. Just sit back, relax, enjoy yourself. Just take some stress out. All right. Frequency in the category / class and divided by the sum of the frequencies. Now, what do I mean by that here? Let's go back to our example here. Now, if we add up these frequencies here, this is very important actually. So if we add up these frequencies, so if we say 1 plus 3 plus 4 plus 4 plus 4, if we add up all these numbers here, we get 16. Now, if you notice here, 16 is incredibly important. Why is 16 important? Because 16 is reflective of the number of data items in the data set, right? You could say we had 16 scores for this test. So the sum of the frequencies here, if we arranged it correctly, should equal the number of data items that were given here in the first place, that being, in this case, 16. All right, so that is something to keep in mind and is very important to go ahead and follow. All right, now as for relative frequency, that's going to be its kind of own little column here. Put it off here to the right. And all we have to do here specifically is we're going to take the frequency of that category or class. I'm going to say that's 1. And we're going to divide that by the total sum of the frequencies here, which is 16. So we go 1 divided by 16 here is what we're looking for here. Now, can anybody tell me what I would like here in this case, by the way, and this is going to see, thank you, Swish, for the follow. That's really super kind of you. What I would like you to ask me here, actually, let me ask you here, is what is the decimal equivalent of 1 over 16? Can anybody tell me here, really? So, I actually do want the decimal here for a reason. So, 1 over 16 as a decimal. Bust out your calculator here for just a second. I don't mind. That's what it's there for. I'll let you guys tell me. 1 over 16. 0.065. Okay. All right. Perfect, perfect. All right, so that's the first one here. I'll talk about this here, why I would like it, and why decimal format here is important. So next one here, let's do 3 over 16. So 3 divided by 16. And I will need a decimal equivalent for that. So let's get a decimal equivalent for that. 0.1875. Alrighty. All right. Excelente. All right. Let's do the next 3 because all 3 of them are 4 out of 16. So let's do 4 divided by 16. All right, easy peasy lemon squeezy. No problems for any of you. 0.25, excellent. And so again, the next 2 will also be the same. Obviously, numbers. So, all right. So why is relative frequency important here? And why did I ask you to put it in decimal format here? Well, the particular reason why I wanted to put it in decimal format here is that each one of these decimals represents a percentage, okay, of how many what the frequency is in each category in the data set. So for example here, just as a quick example here, you say how many what percentage of data items is within 50 to 59 here. Well, you could say that'd be 6.25% as an example here. So if you add up the relative frequencies and you get it, and you're correct in doing out your frequency distribution, is that at the end of the day you add up these decimals here, you should get 1 or 100%. Okay. So again, you can add these up together. Now, mind you, some decimals here, let's just be honest with ourselves. Some decimals are going to be really wild and crazy. If you have maybe not as nice numbers as we have on screen, because maybe you have, say, 3 over 7 or something like that, and you have a repeating decimal, or a decimal that, if you get close to 1 or you get exactly 1, then that means you pretty much did it right. Because again, you may need to round decimals. That may throw off the exactness at the end of the day. So, but if you get pretty close to 1 or you get exactly 1, then that's an indication that you did the relative frequency distribution correct, and you should be just fine. All right, so I just want to let you know about that, but that's essentially how relative frequency works in a nutshell. All right. Okay. Very good. Okay, this is actually that's a wonderful question. All right, yeah, let's talk about that here. Now, certain questions on my math lab would like you to round to a certain number of decimal places. So, again, be careful about what my math lab will ask you in terms of questions. Some of them want like 2 decimal places in certain questions. Some of them want 3, some want 4, 5, whatever. All right. Now, what I place as a standard MO for what we're going to be doing here for most of the problems that we will be doing for the course. I'm going to go back to the handout here. I'll put this down here. This isn't. Round to 4 decimal places. This is going to be our standard MO for pretty much most of what we're doing here for the course, is to round to 4 decimal places. All right. Like I said, my math lab may ask you for whatever, but for the examples that I'll be doing, I'll probably be rounding to 4 decimal places. All right, so a great question there, Alex. That's going to be our MO for pretty much the rest of the course. Okay. Any questions about that? Again, keep that in mind when I'm doing examples about how I'm going to be doing rounding and all. And edit to sad. All right. Okay. So we did answer number 3 here. How do we make a relative frequency distribution? Because in effect, for number 3, this is basically how we do number 3. This is a relative frequency distribution using the formula here from number 2. Just knowing how to do that, not be a problem. Alrighty. Okay, let's move on to the next question here, which is number 4. All right. What type of graphs can we make using frequency and relative frequency? Well, there are several graphs that we can certainly make using the data and using the frequency chart or using the relative frequency chart here that we have for our example. Now, some common ones that you see, probably you've heard of many a times, are bar charts. Okay, bar charts, pie charts, which are pretty common. Line charts. Let's see. Besides that, I'm trying to think of a couple. Right. So there's one called the Pareto Chart. You may or may not have heard of Pareto Chart, but basically, this is basically a descending bar chart. I can't spell that. All right. I'm bad with spelling. It's fine. All right. Yes. All right. So it's descending bar chart. So you start with the biggest bar and then kind of work your way down. That's a Pareto chart. So there are certainly several graphs that you can use here that would be pretty common here that you could use frequency and relative frequency distributions. All right. I'm trying to think if there are any more charts here. I don't think I can't think of any off the top of my head. Those are the most common ones that I can think of. That's what I have. All right. Now, we'll be looking at a couple of these. Actually, oh right. Oh, that's technically a bar chart. Yeah, we'll look at that. Anyway, I digress. Okay, so let's take a good look here at the construction of this. All right, so I'm gonna put split screen here for them. All right. I'm going to split screen this for just a moment. All right. And I'm going to show off here again. You see here on the right is what we just did for frequency, relative frequency. And what we're going to discuss here is talking about number 5, which is what is lower class limit, upper class limit, and class width. Okay. Now, these are very important. As I mentioned here, a category can also be termed as a class. So again, you'll hear this in the textbook here. Class can be same thing as a category. Okay. So each individual score range from 50 to 59, 60 to 69, each one of those is a class, all right? Or group. Yeah, whichever way you want to call it. I'm just kind of going off the books here definition, so it's not like you're caught off guard. But group is also the same thing. I don't mind that at all. Actually, I like that swish, so I'm going to actually just do category / group. I think that's fair to say. 100%, I think you're absolutely right. All right. So, let's take a look at a lower class limit. A lower class limit is the lowest value in a class. All right. Okay, so lowest value in a category, lowest value in a group, whatever the case may be. So you'd say, what would be the lower class limit here? So for example here, 50 would be a lower class limit. Okay, because 50 here, again, is the smallest value that you could have between the scores of 50 to 59. 60 would be a lower class limit, again, being the smallest value between the scores of 60 to 69 in that particular class or category. Call it. Okay, so again, all right, you get the general gist. All right. Now, the upper class limit here is exactly the opposite here. I think you can probably guess here. Upper class limit is the highest value in a class. So again, our examples here are going to be pretty simple and straightforward. Highest value here would be like 59, 69, 79, and so on and so forth. All right. So those values here would be the upper class limit. Now, more importantly here is the class width. So the class width here is very important, right? Why? Because again, class width, what we want to do here is we want to take two categories, okay, or two classes. What we do here is we take the lower class limit. So we're going to take the lower class limit of class 2 minus the lower class limit of class 1. All right. Let me go ahead and describe what that means. All right. You need to sort out an example here. Basically, class 2 would be the class that would be after class 1. So for example here, class 2 could be the scores from 60 to 69, and class number 1 here could be the scores from 50 to 59. I take the lower class limit of class number 2, which would be 60, and I would subtract that by 50. So that's all I'm literally doing here. So if I'm talking about class width, again, that'd be 60 minus 50. So our class width here would be 10. So it's actually not dependent on the upper class limit. It's actually dependent on the class above that one. And then that's actually how you can determine the class width. So probably people, the most common mistake I see people make is like, okay, you take 59 minus 50 and your class width is 9. I said, that's not how it works. Because in reality, how many scores are between 50 and 59? There are 10 scores between 50 and 59, all right, that you can get on your test if you're taking just whole numbers. So that's why the class width here being 10 is very important. Okay. I'll write this down here for posterity. Okay. Yes, between each subsequent class. So it has to be the next subsequent class. That's why I mentioned class 2 and class 1. So that's why it's not the range of the group class, right? So I want to clear up that misconception because it's not exactly all self-contained within that one category. That's correct, Swish. All right. Now, why is this important? Why is this little factoid here fairly important? Let's talk about that here for just a second. And that's going to lead here to number 6. How do we construct a frequency distribution with the proper number of classes? Now, we talked about upper class limit, lower class limit, and class width, but in order to construct this frequency distribution, in order to arrange data appropriately, you have to actually strategize about how you want to set up your table or chart here for your frequency distribution. So there are several rules that we do follow here to set up the proper number of classes. The first and most important thing is that um, the class width uh, must be consistent. Okay, so the class width must be consistent. All right, for every class. So I can't spell. All right. Uh, so what do I mean by that? Meaning to say, if I chose 50 to 59 being my first class, and that has a class width of 10, my next one has to be 60 to 69. If I'm going to ensure that I want a class width of 10, I can, and this has implications. This has very large implications. What this means is that since the class width must be consistent, this is not like I have an option to be consistent. It must be consistent. Okay. So what that means is that, again, you cannot skip scores. Okay, you cannot skip scores here. All right. So one thing is that you can't skip. All right. So even if, let's say, for example, let's say you have no scores in the 60s. Let's say no student got 60s on their test, and say one student got a 55 or whatever. It means that you still need to make a category for the 60s, even if you don't have anything represented in that category. Even if you have 0, you still need to put in that particular category. It still needs to be represented. All right. All right. So I do want to state that here is that you can't skip scores. This is really important here because again, everything has to be represented here appropriately. So again, even if it's 0, it's still a thing. All right. I'm just going to put that out there. That's very important. Also, one other thing about arranging scores or arranging data items, regardless of what you have here, is that you want to have a maximum number of classes. You don't want to have too many classes, otherwise the data is going to get really unwieldy and really, really difficult to work with. So at max, you want 10 to 15 classes. All right. All right. Want max 10 to 15 classes. So you don't want too many classes, okay, because then it just gets to be too much to actually get any information off of. So meaning to say, what does this mean? Let me go back to my data set here for just a moment. What this means is that if we look at the data set, here, I cannot make every single score an individual an individual class. Do not do that. So one thing I think you should not do, not make every single data item a class. Okay. All right, so this shouldn't be like 70 has one, and then you skip to 72 that has one, and you skip to. No, you can't do that. All right, that is not something that you're allowed to do. All right, that is something that, because again, there's no consistency in the classes, and you're just skipping stuff around. All right, so, and you're going to have too many classes at the end of the day if you make every data item a class. So it just is way too much, and you're not going to get any information out of it that you may need to make conclusions off of using that strategy. All right, so hence why the max you want to have is like 10 to 15 classes, especially if you have, most of the time in a realistic setting, maybe not this setting here because it's, just 16 test scores, for example. But let's say you have thousands and thousands of data items. Let's say you're in a company or running a corporation, and you're like, okay, you have thousands of these customers, and you arrange them in such a way where you want to classify them in certain categories. Well, having thousands and thousands of categories for customers would be crazy. You probably would want to categorize those customers into maybe 10 or 15 categories, and it would be easier to go ahead and arrange them based on that, based on whatever designation you put them in. So um, that is, again, another reason why we want to limit the amount of classes or categories on here at the end of the day. All right. So I did want to make that point here. It's, again, probably the most common thing people do. Want to like, oh my god, I could just do that. Like, yeah, no, that's not how it works in stats. Sorry. um, that's a no. Okay. Any questions so far before we move forward? Any questions? No question mark. Okay. No. All right. Okay. Let's go ahead and take a look here at the very next question. Okay. We'll need to go back to our little paint tool here or do that here. So number 7, what is a histogram and some property? Okay, so first of all, let's talk about what a histogram is. All right. What's the definition of a histogram? So a histogram here. Oh yeah, stem and leaf plots are fun and easy. I promise you that. Super simple. Um, um, what's a histogram here? A histogram here is a connected bar chart. So it's a connected bar chart that represents the frequency distribution, frequency or relative frequency. All right. So the key word here, it is a connected bar chart. Okay, meaning to say it's not a separate bar chart. You don't have separate bars. They're all kind of connected together. All right. And again, this is going to represent the entirety of the data set. Okay. So we're going to take a look at that. We'll talk about a property or two that come along the way. But let's go back to our example here. Make this screen now. All right. And let's construct the histogram behind this frequency distribution. Alrighty. Okay, so what we're going to look at here specifically is we're going to go ahead and take a look here at, again, we have frequency being 1, 3, 4, 4, and 4. So what we need to do here is specifically is we need to go ahead and we're going to make this a smidge bit. Go. Is we're going to start off with a little chart over here. All right. Now on the bottom here, we're going to have our scores. And then on the left here, we're going to have our frequency. So frequency on the left and our score here on the bottom. Now each category has to be represented. Like I said, even if it's 0, still gotta represent that category here. So our scores here specifically, we're going to start off here with this tick mark being 50 to 59. Start off here from 60 to 69. Okay, then we'll do 70 to 79. Do this 80 to 89. And then finally 90 to 99. Okay. So that's what we have here in this instance. Okay. So now that we have that, all we need to do is represent each one as a bar. Now the first one here is 50 to 59 here, which has a frequency of 1. So let's put our frequencies here over to the left, by the way. I forgot about those. Sorry about that, everybody. 2. So we start off here a little bit to the left, okay, of 50 to 59. Notice what I'm doing here. I am not starting here directly from the left. I'm starting off here to a little bit to the left here of the tick mark for 50 to 59. So we'll put this in red here. I'm going to start here. I'm going to go up to 1. And then I'm going to go a little bit to the right of 50 to 59. And I'll bring that down just like so. All right. That is the first bar here of our histogram for 50 to 59 with a frequency of 1. Now, the next one here is 60 to 69. Remember, though, in the terms of the definition of a histogram, is that it's a connected bar chart. A connected bar chart. So because it's a connected bar chart, we're going to bring this up here. We're going to start here from the upper right-hand corner, go up to 3, go a little bit to the right of 60 to 69, bring that down, and there we go. We have our second bar here, which is our 60 to 69 category, and we have our frequency here of 3. Next, we do 70 to 79. Again, that's 4. We start off from upper right-hand corner or wherever, and then we just work our way up to 4 and repeat this process. There we go. That's 70 to 79. There we are. All right. Next is 80 to 89. Start off here. Go to the right by 4 since it's the same thing. Same thing with 90 to 99. And this is our histogram length. All right, any questions about that? Here is our histogram for our frequency distribution for our example. Okay, so what's one property that we can certainly take away from this? One property that we can certainly take away from this is that, let's talk about one property, probably, is that that we do not start the histogram directly from the left, unless this is only unless if we have 0 part of category slash class. Okay. So we do not start directly from the left here. That is a property of histograms. Again, it is a representation of the entirety of the frequency distribution. All right, so definitely something to keep in mind here. Construct this histogram and put it together. All right, so as you can see here, not too bad, pretty straightforward. All right, it takes a little bit getting used to because some examples in the homework here will be a little bit tougher to deal with. But again, you just have to read it carefully. And the only reason why they're tough to deal with is because the bars are kind of small. But if you construct it like this, it's much easier to see. So you can also see that the midpoints here of each of these bars are the actual categories. All right, good stuff. All right, easy peasy lemon squeezy. Okay. All righty, good job. All right, so That will be number 7. Now, we have gone for almost an hour, so it's almost noontime. And as always, we'll take a 5-10 minute break here, just like we always do. So let's take a short 5-10 minute break, and we're going to come back at 12:10. We'll come back at 12:10 p.m. here. And we're going to go ahead and finish off the rest of this handout here and talk about a couple other things here for the latter half, okay? So let's come back and continue moving forward, okay? I'm going to go ahead and hit a splash screen here. Oh, I guess I'll need that too. Hang on. Oh, that stopped. This is mine. All right, we'll be back, everybody. watch a. I'm going to AEW Dynamite tomorrow. That's where I'm going. It's my first wrestling show. I'm gonna go watch AEW Dynamite tomorrow. Going to the Now Arena down the street. So, and hopefully I will get to see CM Punk, which will be just unbelievable. Like, I want to go see CM Punk so bad. Oh my god. CM Punk's like everyone's hero. It's amazing. Yeah, I love wrestling. It's super fun. Wrestling is just super enjoyable. Like, for a long time. Oh, you working this? Oh, there you go. Yeah, it's gonna be super busy for you tomorrow, Jasmine. Gonna be a ton of people. Like, that whole weekend at Now Arena is gonna be absolutely bonkers. I ain't gonna lie. It's gonna be absolutely bonkers because they have Dynamite on Wednesday, and then AEW is gonna be doing. This is all at the Now Arena, by the way. Dynamite on Wednesday. They got Rampage and tapings on Friday, and then they have the pay-per-view all out on that same weekend as well. You see the SmackDown. Look, SmackDown is not terrible. All right. I mean, don't get me wrong. I like Roman Reigns. You know, I like the whole head of the table thing with Paul Heyman and stuff. So I'm not gonna lie to you. Yeah, AEW is just like, it's a whole nother thing. It's so different. It's a lot of fun to watch. It's just, you know, if you want to see silliness, you want to see absolutely, you know, just having a great time and just being entertained. It's just like that. You know, it kind of goes back. It's like a good throw. It's so fun. Yeah, Jasmine, it's gonna be really, really busy. If you work right next to the Now Arena, don't be surprised. So, I would say if I don't know what time you work, Jasmine, or any of that stuff, but yeah, the show's gonna start in the evening, but they're probably gonna open up the parking lot at about 3:30. I think they said 3:30. So, if you have to find parking, then you know. Yeah, yeah, there's gonna be a flood of people when you get out at 5:30, because they're all gonna try and get in the show, because the doors are gonna open at 5, and then the show starts at 7, so it's gonna be pretty busy. So make sure you get out safely from that area. All right. Yeah, you gotta book it. Like, there's gonna be so many people coming. It's crazy. Like, every single show is sold out at the arena. Every single show. So, it's not gonna be one of those, oh, there's just a few people coming in for, like, monster trucks and stuff. No. It's gonna be completely sold out every single day of that weekend. It's gonna be absolutely bananas. At least Thursday they're not doing much, and so. All right, now let's go to the big board here. I gotta finish this off at the very least. All right, next, what? Let's take a look at number 8. We talked about histograms here, so we now know what histograms are talking about here. Let's go ahead and finish off the rest of this handout. Let's take a good look here at number 8. Number 8, what are stem and leaf plots, and what are some things to remember? Okay, let's take a look at stem and leaf plots here. They're not too hard, but we're going to do a stem and leaf plot here with the given example that we already had talked about here earlier in the first half of class. So we're going to once again go to the well here one more time, talking about a stem and leaf plot here. This time, though, for us to focus on the stem and leaf plot here appropriately, I'm going to zoom out here because the specific reason why I'm going to zoom out here is because of the fact that we want to be able to look at the data set here. So we're not, in this case here, the histogram deals with the frequency distribution. But the stem and leaf plot here deals with specifically the actual data items within the data set. I'm going to add that here also in the thing here. Okay, but like I said, there's two sides for every stem and leaf plot. We have the stem, and so the stem here would be, say, the tens digit. And we have the leaves. And the leaves here would be the, say, the ones digits. So I'm going to go ahead and put that here in. So talk about the stem. So again, remember here, this represents every data item in the data set. All right, and this is going to select, again, the stem here typically is the tens digit, or a digit of some kind. All right. So let's take a gander here at this. Okay, so if I were to look here at 6, let's go in order here. Sorry, not 6. Let's go in order here. We have 50s, 60s, 70s, 80s, and 90s. And again, one thing to remember here is that even if there's nothing represented in that group for the stem and leaves, you still have to represent that. So I actually should add that too as part of our notes. So every stem must be represented even if there are no leaves. So you have to be consistent. You can't skip. Again, just like class width when we talked about categorization, you can't just randomly skip and then be consistent. No. Even if there's no leaves, you still have to represent it. That still has to be a thing. Okay, so I just want to make a note here regarding that. Okay. All right, good stuff. So let's go back to our example here. All right. So here we have stems. Here we have scores in the 50s, 60s, 70s, 80s, and 90s. Okay. That's what we have here in this case. So if I talk about scores in the 50s, I take a look here and I say, well, okay, I have one data item here, or one test score that is, in this case, 52. So in my leaves here, I would put 5, and then I would put the number 2 here, all right, for 52, right? That's how I would represent 52 as a data item in the data set. All right, so let's take a look at 6. All right, what numbers would I put in here for leaves under 6? Because as you see here, I have 3 scores in the 60s, so I should have 3 leaves here. What leaves should I have for 60s? Let's go with 67, right? So I'll put in 1, that'd be 7. 7, 1, and 9, okay, good, right? All right, good, because we have 67, 61, and 69. Now, just to let you know, you don't have to necessarily put it in numerical order, not for setting up a stem and leaf plot. Now, it is helpful to put it in numerical order. I ain't gonna lie about that. That part is true. But you don't need to put it in numerical order for these examples anyway. This is just fine to put it out of numerical order since we're just reading directly off of the data set. Okay, so no big deal here, but for what we're probably going to be doing here later on, yeah, we're going to be putting in an order anyway. So, but just letting you know, for these examples, it's not going to be like super harsh. All right. What about 7? What are our leaves for 7? We have 4 scores in the 70s according to our frequency chart. So what scores are in the 70s? What should our leaves be? 3, 5, 7, and 8. Very good. That is correct. Good, good. Nice. All right, so you could go again. You have 78, 77. All right. All right, you have again so you're 73 and 75. So that's correct. Good. All right, let's talk about the 80s here. Now, I'm going to talk about this in order of what we see. So actually, let me ask you guys, what numbers are we going to put in for our leaves for 80s, for the scores in the 80s? We have 4 scores in the 80s, so okay, both are correct. Good, good. Okay, so we have 80 here. Nice. Okay, go ahead. Ask a question. If you're confused, I'm here to answer your question, okay? What are we confused about here, my friend? Ask away. So let's go over this here carefully. So hopefully this clears this up. Okay. So if you're confused about how we're getting these results, let's go over this very carefully here, all right? So for the 80s, we have 82. So this 8 here represents the tens digit. This would be the 80 part here. Since this data item says 82, then the 2 here would be my leaf. Okay, so 82. All right, that's how I would read this. 82. Then the next 80 score is 88. So I have 80, and then I put here as a leaf at 8. And this would represent 88. Okay, that's how we can get our leaf there for that particular guy. Our next score here is 80. So that's 80, and then a 0 would be your ones digit. So that'd be 0. So A0, 80. Right? And then the last score here is 82. Now, even though this repeats, you still have to represent that. And that's another thing that I do need to make a note of here, and I was going to talk about, is that we have 82 here. So even though 2 repeats, we're representing every data item in the data set. All right? All right, that is the most important part here as a stem and leaf plot, is that every data item in the data set is represented. So the other note that we can put here, of course, is that note number 2. Note 2 is that leaves and repeat. That is perfectly fine. Leaves can repeat as many times as they want. All right. You can arrange the leaves randomly in this case. Now, for what we're going to be doing here later to answer that, Kamar, is that we have what we want to be doing here is we're going to be putting in an order here when we talk about the latter half of this particular chapter, because we're going to be able to get some information a lot easier if we do put them in order. For the purposes of these examples, you don't have to put them in order here. So you can arrange them randomly for these examples, but later on we're going to see where they are put in order here, and then we can get some information when they are put in order. So basically, at this stage, you can do either one at your leisure, but for later on, we'll put them in order. All right. Let me know if you have a question about that. I hope that makes that clear about what the expectation is, at least. Okay. Okay. Next, let's go over the 90s. All right. Let's go over the 90s. What about the 90s here? Let's go over this here. We have 93. So we have 9 and 3 here for our leaf. 91. All right. So 3, 1, 7, and 4, right? So 91, 97. Okay, agreed. And then 94. There we go. Got it. Jeez. Give me a second, guys. Hang on. What is going on out there? Uh-oh. That's bad. Be right back. Oh dear, here we go again. That thing's gonna go off forever. Fine. I don't know what's in there, but hey, that's my laundry machine for you, ladies and gentlemen. Alright. Alright, so let's take a good look here. What are we gonna, if there are no leaves, what are we gonna put in there? You don't put anything in there. So if I said, if I had like, say, let me go here for a second. If I had, say, another leaf, let's say I had 10, represent like the hundreds, for example, well, then you would just put nothing in there. And then that would be representative if there are no leaves. Alright. Yeah, so if you still need to represent a stem if there are no leaf values, then what would we put in that column? Yeah, so that's exactly how we would want to take this. It would just be nothing in here. So let's say there were no scores in the 60s, right? Let's just say there are no scores. Then there'd be nothing in here in the leaves. But you still have to represent it because it is still part of the frequency distribution. Again, this would represent in the frequency distribution, you say, okay, the frequency is 0 because there's no scores in, say, the 60s as an example, right? All right, so, but you would leave this blank, but you'd still have a stem that represents 60s, all right? So that's how you would do a stem and leaf plot there, all right? Okay. All right, so that's how that will go essentially. All right, any questions about that? No. Okay. So for the leaves for 9, how'd you get 7? So 7 came from 97. So again, 93 for this first one, 91 for the second one, 97 for the third one, and 94 for the fourth one. So that's how I got 7 for that leaf. It's in the data set. So go through each one of those data items very carefully, and then you can go ahead and write those down. That's how I got the 7. All right. Let me know if that hopefully answered your question there. That wasn't too bad. Okay. All right. Cool. All right. Let's move on here to the next part. All right. Okay. Now the next part here is really important, and so I do need to talk about this here because it is something that we're going to see here later on, and we'll be discussing in a lot more greater detail in this course. That is talking about the shapes of distributions. Okay, so what are some shapes of distributions? And so in basically, shapes of distributions are pretty, there's going to be 4 pretty much basic shapes of distributions that we're going to be seeing. Now, of course, I can't put it here for that question, but we're going to need a space here on the canvas, but these basic shapes of distributions, right? So the 4 types of distributions that we are going to be looking at here in this course, and one of them is pretty much more important than the other 3. So let's take a look at the first one here. Now, let's say we have some histograms. So what I'm going to draw out here is some basic histograms, all right? To put put this first one here, just like so. So this one here is basically what we call a uniform distribution, right? Just pretty much flat across the board, all right? Everything has the same frequency. You know, it says all the frequencies are 2 or whatever you want, okay? So a uniform distribution is pretty straightforward. There you go. It is what it is. Flat, easy peasy lemon squeezy. All right. Okay, let's go over the next one here. All right, so this type of particular distribution is what we call skewed right. Okay, so we call this a skewed right kind of distribution. So the reason why this is called skewed right is because the tail of the distribution is basically going to the right. So that's why we call it skewed right. All right, so the tail is really what they look at here, not where the bar is the biggest, but really where the tail of the distribution is. So they call this skewed right. On the flip side here, all right, so this here is what we call a skewed left distribution. Again, same reason, the tail of the distribution is off to the left. Okay. And now, the last type of distribution, and probably the most important type of distribution that we're going to encounter here, is going to be this distribution. Now, this distribution here is what we call a normal distribution. This also has another name of like a bell-shaped distribution, so kind of a couple names. Now, this normal distribution is something that we're going to explore a lot of here in this class, okay? We're going to be looking at a lot of different properties behind this normal distribution. This is like basically a type of distribution that's the most ideal kind of distribution that we want here in statistics. This is like the super ideal, all right? Is kind of like a bell-shaped curve or a bell-shaped kind of distribution. If you want to think of it this way, the easiest way to think about a normal distribution is like back in the day, way back in the day, educators thought that having the best kind of test that you can make for students is if you get results here that resemble a bell-shaped distribution, meaning to say a bell-shaped curve. So essentially, a few students got A's, a few more people got B's, the majority of people got C's, same amount of people who get D's got B's, and the same amount of people who got A's got F's. Okay, so again, that was the ideal test. Now, do I agree with that? No, but that was an example that that you can kind of use here to talk about where a bell-shaped distribution is effective. All right, so that is a normal distribution. We'll be looking at a lot about these normal distributions here in greater detail. I guarantee you, it's really not too bad. All right, so it's pretty straightforward in my opinion. It's pretty easy. Okay, good stuff. Okay, let's see here. It's all about. Okay, now you got a good idea about what these graphs look like. All right, let's go ahead and move on here to the next question. It's for 9. Okay, next question here. What is a time series plot? Okay, so what time series plot, something that we're not going to talk about too much, but a time series plot basically is a graph that represents a, actually specifically I should say, excuse me, a line graph that represents a stretch or period of time. Probably the thing that talks about a time series plot, the best example you're going to ever find is a stock chart. So you talk about a stock chart is probably the #1 example here to represent a time series plot. So if we take a look here, let's go ahead and take a look at a stock chart here really fast. So let's bring up the S&P 500. Okay, so this is a stock index. All right. Or actually, we could also take a look at Apple. Let's take a look at Apple. Like Apple. So let's look at Apple. This is Apple today, but maybe I want to look at a time series plot into Apple stock. So I take a look, let's say, how has Apple stock performed in the last 6 months? And then this is, the past 6 months, this is what the stock has looked like. All right, kind of going up here to, it's like $152. Or again, if you want to look at last year for the past year, here's Apple stock for the past year, the past 5 years. Okay, you get, the, 10 years, whatever you want, or like all the way back to its inception. So, okay, you get the general gist about how it works with things like Apple or like. So, it's not too hard. It's pretty straightforward. But again, time series plots, probably the easiest one is always stock charts. Simple stuff, I promise you. All right. All right, so that is talking regarding that. All right, any questions about that so far? Got one more question to do. Any questions so far? Alrighty, here we go. All right, nope. All right, so the last question that we're going to do here today is going to be the first question from the next handout, which is just basically section 2.3 in a nutshell, and then we'll do the last half here. So, how can graphs be misleading? Now, one of the things that we'll talk about here is misleading graphs and the representation of that misleading graph. So, graphs can be certainly misleading. Again, statistics can be certainly misleading. This is, people know this, okay? This is not something that I'm not unaware of. Even though I teach the subject here, I want to teach you at least the proper way to arrive at the statistics. But one of the things that is important, of course, is to arrive at conclusions based on the data that you see. All right. Now, of course, sometimes you present graphs or statistics in a way where it seems to shift a narrative or it seems to shift an opinion toward one particular point, and hence why you have misleading graphs that can certainly change your perspective in that general direction. The goal here is to basically see how we conceive graphs can be misleading and what to look out for if you ever do read a graph in order to make sure you avoid that kind of bias. Again, I like to take things from a non-biased, as much of a non-biased perspective. I'm not going to say that completely non-biased, but see the data for what it is. So let's take a good look here at one of my favorite examples about how graphs can be misleading. Let's take a look at the very super classic example of the absolute worst pie chart in the entire planet Earth. All right, this chart here is a chart that actually was shown on television. This is a true chart that shown on TV during the 2012, presidential run thing. So I want you to take a look at this chart here. All right. I want you to tell me, taking a look at this pie chart that you see here, what is wrong with this chart? Why would this chart be misleading? Let's talk about, presidential candidates here, in this case on the Republican side. They had Mike Huckabee and Mitt Romney and Sarah Palin running at the time, and talk about their support, whatever. All right, so they add up to more than 100%. Okay, that's true. That's one thing. Trust me, neither did I. What's another problem here? I agree. Percents add up to more than 100, so that makes no sense. What's another problem here? There's a couple more problems here with this graph. That's right. The scaling for 63 is larger than the 70%. So first of all, the scaling makes no sense either for the portions of the pie. I totally agree. All right, what's one more problem here that you see? There's one more problem here. Maybe you're not sure about this one. So if you don't get this one, I'll fill you in. There's actually one more problem with this. So the scaling is number one. The percentage is adding up to 100. Obviously, it's way more than 100. All right, scaling for the portions of the pie. That's also pretty bad. The actual last part is that there doesn't seem to be the source, right? So, right, there you go, the source. All right, so the source. So we have issues here. Is that you have to be very aware. You have to be very aware about what you see in front of you. Imagine if this flashes on a screen for like maybe 10 to 15 seconds. Well, it's tough to make an opinion based off of that, but that's why I say, stop and smell the roses. Take a look at the graph. What are they trying to tell you, and what's the reality behind that situation? So one of the things is that I guess I could say here specifically for this question is to again be careful. Yeah, that is. Be careful about scaling, proportions, uh, proportions, and sources. This is very important here to make sure that you're not misled into the wrong conclusion. Definitely, this is one of them that certainly you can say for a fact. Let's take a look at another chart here. And again, by the way, this doesn't apply to just everyone. So this applies to pretty much every news, but these are the most classic ones. Let's look at this one here. Actually, yeah, here. Which one is? Yeah, here's the one. What's wrong with this? What's wrong with this graph that you see here on the screen? What's wrong with this particular bar graph? What do you see? This talks about federal welfare received in the U.S. Okay, so this talks about the number of people who receive the, I guess, welfare. They don't have a label on the bottom. Okay, that's certainly, yeah, I could take, yeah, that's true. All right, what else? What else do you see there? Take a look at the left. What's the problem? What's the problem with the left there? That's true. Not everybody's supposed to participate, so that's fair. Actually, I will give it up to Fox for that. It's like, you're gathering a sample, as we talked about here previously. Okay, so you will be gathering a sample here. Be like, all right, fine. You're grabbing a cross section of people. All right, good. So you're starting at 94 million. You're not starting at 0, right? You're not starting at 0. You're starting at 94 million. So it looks like it goes up a little bit, and this very well may be true. But again, the problem is that it starts at 94 million. So it's a little more subtle of a misleading graph instead of looking at it from a proper perspective. All right. This is one of my favorites as well, because this is probably one of the most poor. This is a really poor one because of the fact that you go up from. Take a look here. This one's actually really bad because the scaling on the bottom here doesn't match up in terms of time difference. Like December 7th to September 08, you magically go up 2 million, then you go up 4.5 million. So again, in the scaling here, it's just, and it's supposed to be linear. That makes no sense. Okay, so again, a way you can see how misleading graphs can certainly change your opinion here. But like I said, by the way, like I said, this doesn't apply to this doesn't apply to just Fox. Now, Fox, of course, is pretty famous for this. All right. So we could talk about, say, MSNBC is the same thing, and both sides of the, it's both sides of the aisle, folks. So I'm not gonna lie, it's both sides of the aisle. Let me show you a graph here like this. Like this graph here is this graph here is pretty poor. I don't like graphs like these, like, oh, the change in U.S. poverty rate has suddenly magically gone down 40%, you know, all in 1 year. Like, this is the representative. So I don't care which side of the aisle you're on, and I'm not here to talk about politics. What I am here to talk about is that, you know, whichever side, what kind of narrative you're trying to push, whether it be a left-leaning agenda, right-leaning agenda, it doesn't really matter. Both sides employ these tactics regardless. Okay, so it's not just Foxes, it's everyone. So you got to be on the lookout for these sort of things, and you got to be able to discern the data and kind of read between the lines a little bit in order to make sure that you don't get taken advantage of based on and you know, push towards some kind of conclusion there. It's like saying, think of it this way, right? Let's think of it this way. Oh yeah, I know. You remember how there's certain movies on Rotten Tomatoes, for example, where all the critics say that the movie is absolutely fantastic, but then everybody else who actually went and actually saw the movie said the movie is actually total garbage. All right, so like the critic score could be like 90%, but the audience score is like 25%. All right, that's a place where things can be certainly misleading. How many people have seen movies like that, you know, or at least heard of movies like that? I've heard of a few movies that are kind of like that, where basically the studio probably bought out the critics and basically tried to make them look really good, even though it was completely trash. And so at first blush, right, you probably see like, oh my god, every critic saying, oh my god, this movie is so good, boom, 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 boom. Okay, and you're like, oh, I'm so looking forward to going to see this movie. And then you go ahead and see what the real reviews are. You're like, oh man, I just wasted my money and time. No. I don't know what I remember hearing about a couple movies. I think it was let's see. Let's go to Rotten Tomatoes. I forgot that there's go to Rotten Tomatoes here. There's certainly some movies that are probably like that. He's all that well. There you go. Vacation Friends. That just sounds terrible. Let's see. What would be a good movie here? I remember a couple. I don't remember. There are some movies that actually had that there. So anybody can give me an example? Yeah, class goes to, oh, I've been overtime. I'm sorry, my friend. Sorry, I went a little overtime. I thought it was 12:50. Might be. Yeah, but I know that there's some movies here. I'm not gonna force you to any right now. All right. Yeah, I did go a little overtime here. I apologize, Vince. My apologies. All right. Okay, so that is that last one there. That pretty much is like section 2.3. There's not a whole lot in the section 2.3 outside of just kind of like that. Now, what we're going to be doing here next time on Thursday is we're going to be going ahead and doing the last part of chapter 2, and we'll be doing a little bit of chapter 3 as well. So we're going to be slowing things down a little bit, but I do apologize for going over a little bit of time. Thank you, Vince, for letting me know. All right. So I want to thank everybody here for coming out here to the stream once again. You guys are absolutely fantastic. All right. Thank you so very much for coming on out here to the stream. You guys, I love you all. You guys are wonderful. All right. I hope you guys enjoy the next couple of days. I'll let you know how Dynamite went. And I hope to see you all then. All right, what's the homework? Go up to chapter 2. Okay, so do the chapter 2 homework there. All right? All right. Thank you, Jasmine. I really appreciate that. All right. All right, we will see you there Thursday. All right? And as always, everybody, stay safe, stay healthy, but most importantly, stay sane. All right? Have yourself a wonderful day, and we'll see you then. Thursday, same time, same place. Upcoming assignment here will be chapter 2. Okay, so chapter 2 will be the assignment. So do all the sections. All right. Okay. All right, have yourself a great one, and we will see you then. I don't expect you to do, actually, we'll do 2.1. All right, here we go. All right, have a great one, everyone. All right, see you then. All right, take care, everybody. All right. Bye. Bye, everybody. We'll see you later.